Welcome to the Sargassum Champions Course. You are currently tuning into one of the videos produced for this course. Funding for the course comes from the Resilience, Sustainable Energy and Marine Biodiversity Program, RESENBID, financed under the 11th European Development Fund, EDF, Caribbean Overseas Countries and Territories Regional Program. RESENBID is being implemented by Expertise France, with the primary stakeholders being the 12 Caribbean overseas countries and territories. Let's get ready to learn together.
Welcome to today's session for the Sargassum Champions Course, but also for the Sargassum podcast. And today we invited Dr. Rick Lumpkin, who's going to tell us a bit of where does this big Sargassum belt actually come from that is now impacting the Caribbean and the wider area of the Caribbean and also Africa. Dr. Rick Lumpkin is the director of the Physical Oceanography Division of NOAA, the National Oceanographic and Atmospheric Administration. Not of all of NOAA, but their research laboratory in Miami, Florida, which is called the Atlantic Oceanographic and Meteorological Laboratory, or AOML. Rick, it's really nice to have you here again after you've been on the podcast before. And I leave it to you to answer this really important question that people always have.
All right, great. Thank you very much. It's nice to be back. So I prepared some slides I am going to show to kind of explain what formed the Great Sargassum Belt. And I'm drawing a lot of material for this from this paper that you see cited here. I was the second author. The lead author was Libby Johns, and we had a number of collaborators around the world on this paper. So ordinarily, and for centuries and centuries, of course, a lot of Sargasso has been seen in the Sargasso Sea, the region right around here. But what was really new was what was seen starting in about 2011, when there was this large amount of Sargassum in what's now being called the Great Sargassum Belt, which stretches off from the coast of Africa to the Western Caribbean over a distance of approximately 5,000 miles. So that is really new, and we wanted to understand why. Here's what it looks like, by the way. There's a ship, a NOAA research ship, sailing through the Great Sargassum Belt just last week. They were stopping and starting along the way, and basically spent 5 days crossing through the Great Sargassum Belt. So you can see what sargassum looks like in this belt. It's not one continuous coverage, but rather long rows of it, like you see here, with clear spots between those rows. So here's the ordinary situation when you look at things averaged over a long time. You see in winds that we have the westerlies blowing up in the northern part of the Atlantic from east to west, from west to east. They come from the west, so meteorologists call them westerlies. And then the trade winds blowing the opposite direction further south. The winds tend to accumulate objects at the ocean surface here in the Sargasso Sea. And when you look at ocean currents, which are these little arrows, you can see that also tends to swirl around the Sargasso Sea, with the Gulf Stream flowing to the north, the Canaries current flowing along the coast here, and the North Equatorial current then kind of flowing back around this way. So I work with the Global Drifter program. It's a program to track ocean currents and measure temperatures and other parameters. You can see what a drifter looks like as a schematic on the left. They're tracked by satellites, and they have a large thing attached to them called the drogue that makes sure that they follow ocean currents and not just being blown by the wind and pushed by the waves. And here you can see me holding one with my team here, so you can get an idea of the size of these drifters. Now, after they're in the water for a while, they will tend to lose this drogue. And at that point, they're floating right at the surface, a lot more like sargassum actually is. So one of the first things we wanted to do looking at this, the drifter data, is to understand where sargassum might have come from that ends up entering the Caribbean Sea. So I took all of the drifter data and was able to calculate statistics running backwards in time. The colors here are kind of a probability, and -6 would be 1 million times less likely than where it's red. -10 would be forget about it. You're never going to find it there. And the white is just the 0% chance. So if you start off here in the western and the very eastern edge of the Caribbean, and you run backwards in time using drogued drifters, you will see that it's almost certain that it came from the Great Sargassum Belt. And there are previous studies also using drifter data that basically concluded there's no way that that the Sargassum entering the Caribbean Sea could have come from the Sargasso Sea. The Caribbean in Sargasso don't have this very strong connections, just minor little bits and pieces like what existed before 2010 or so. However, a lot of people hadn't looked at the data from those undrogued drifters, the ones that lost their drogues. And when you do a same sort of experiment running backwards in time, you see that the probability forks in two directions. That indeed, there's the chance that it came from the south, but there's also a very large chance that it could have arrived from this area off of the coast of Europe and Northwest Africa. So that's really interesting, and that gives us a clue that the Sargassum could have come from here. But how do you connect the Sargasso Sea to this area across the other side of the Atlantic? To explain that, we have to talk about a climate fluctuation called the North Atlantic Oscillation, or NAO. This is a natural resonant mode of the North Atlantic climate. Now, to understand what a resonant mode is, you can imagine taking a drum and striking it with a stick, and it'll start vibrating with certain patterns and certain frequencies, as well as make a noise. That's a natural resonant mode of the drum. And if the drum is shaped differently, it could have different modes of oscillation. Or if you hit it in different spots, you might get different modes. So this particular mode is a mode that exists in the atmosphere at very high frequencies, say from days to weeks. But at longer frequencies, at longer time scales, it's also strongly affected by the ocean. And at really long time scales, it might be coupled between the ocean and the atmosphere. You can derive an index for how strong the North Atlantic Oscillation is by looking at the pressure difference between the high pressure that's over the Azores Islands and the low pressure that's over Iceland. And this oscillation goes back and forth between a positive phase, and here you're seeing the temperature changes that are associated with that positive phase. This happens to be January through March 1990 temperatures. In the positive phase, the low is very low, and the high is abnormally high, so the difference is stronger. That tends to shift the winds to the north, create cold temperatures over the North Atlantic, and warmer temperatures over Europe and America. In contrast, in its negative phase, that gradient gets reduced. So the difference between the low over Iceland and the high over the Azores gets weaker. And in that case, you get warm temperatures over Greenland and northern Canada, and colder temperatures across the middle part of the United States and Europe. When we look at a time series of the North Atlantic Oscillation, which we can derive, like I said, by this pressure difference, and we look from 1900 all the way to 2020, if you average it over the year, you see something very dramatic in 2010 right here. You see one of the strongest negative NAOs we have in the entire record. When you look at that on a monthly basis, month by month from 2008 to 2018, you can see that it was really, really strongly negative in December 2009 through February 2010, and then became negative again in 2011. Again, this is the strongest sustained negative NAO that we've seen in the record that we have going back to 1900. So this is it was a really dramatic event that happened then. Here's what that did. Here's what the January, February, March winds on average look like over the period 2008 to 2015. So you can see the Sargasso Sea highlighted in this area here. Again, it's sort of right where the winds are the weakest, with the westerlies here and the trade winds here. However, during January, February, and March of 2010, that very strongly negative NAO shifted the westerlies to the south. It shifted it to basically have strong winds over the northern half of the Sargasso Sea, where Sargasso normally accumulates. You can take the currents derived from ocean models, and then you can add 1% of the wind. And the reason we think 1% is the right number to add to see what Sargassum would look like is that we've done this looking at matches with where sargassum actually is and can be traced, and using drifters that are shaped like sargassum itself, as well as the undrogued drifters. And we see that they basically follow the currents plus about 1% of the wind speed. Here's what the average looks like over the longer time period. And you can obviously see all the arrows kind of point in towards the Sargasso Sea. Everything wants to carry the Sargasso right into the center of the sea. But here it is in the bottom during January, February, March of 2010. And you can see that a lot of the Sargassum would have been flushed out of the northern Sargasso Sea and across the Atlantic to the far eastern Atlantic. At that point, it would get picked up by the climatological currents, which head this way, southward, and then westward, and bifurcating here as well to create also a branch that heads into the Gulf of Guinea. So what we believe happened is that in the winter of 2009 to 2010, this large amount of sargassum was flushed out of the sea, and ultimately by 2011 reached this current area in the Great Sargassum Belt, establishing this great belt. And in subsequent years, it's basically been able to bloom as it's given dust from the Saharan desert. It's given nutrients that upwell in this region where the trade winds diverge, called the Intertropical Convergence Zone, and fertilizer, especially fertilizer that may come from land runoff and major rivers that could pour into this belt. Now, it's really important to note that while this has been established since 2011, it's not the same strength from one year to the next. Here you're seeing a figure from University of South Florida's Sargassum Outlook Bulletin. And so you can see what they've done is picked out the frequencies in satellite images that correspond to that orangish brown color of sargassum. So you can really see where the sargassum is. The brighter red, the more there is. So you can see one year is not exactly the same as the next. 2018 was a particularly strong year, 2019 as well. 2021, and now 2023 is another strong year, but not the highest year on record for February. But there's a lot of sargassum out there, and what that's doing can be traced in our sargassum inundation reports. So in collaboration with other parts of NOAA and with the University of South Florida, my laboratory, AOML, has created this experimental sargassum inundation report where we show where the risk levels are high based on sargassum being offshore. And we also show ocean currents. So you can see what the situation looked like here in the beginning or towards the end of January of this year. And these orange colors are places that are in moderate risk of sargassum inundation, and the red area is high risk. And then you can see the ocean current. This is the loop current that flows out from the Western Caribbean through the Yucatan Channel and then loops around, hence the name, and creates the Florida current and goes on to be the Gulf Stream. So as we step forward in time, you can see how the situation evolves. We go into the very beginning of February, and now you start seeing a large amount of sargassum entering the Western Caribbean Sea, and a lot of the inundation risks greatly increasing along the Yucatan Peninsula. Now, a very large amount of it is in the Western Caribbean. You see these very high inundation levels along the Yucatan Channel, and you see parts of this patch being shredded by the current and pulled into the Gulf of Mexico here. By the middle of February, it was bifurcating, some of it going into this large whirl right here, which eventually didn't come back around and return, and some of it going directly across this pipeline past Cuba, the Florida Keys, and creating large inundation risks along the Keys in Miami. February 21 through 27, you see a relatively large amount being shredded off as more of it accumulated. And we step forward in time until this most recent week here. So at this point, there's still quite a bit of sargassum in the Caribbean, and parts of that are being shredded off, and you can see continuing to loop around through here. Now, there's the chance that this ring here might pinch off and create more sargassum risks elsewhere in the Gulf, while some of it will continue to flow around through here. But we also know as we look upstream, and we can see those in the satellite image as well, there's still an enormous amount entering the Caribbean from the main part of the Great Sargassum Belt, creating very high risk levels for a lot of the Windward and Leeward Islands. And we can see that stretching all across the Caribbean. So this will be a continuous kind of long-term event, we anticipate, where we'll be seeing this flow continuing to create high levels of inundation possibility along a lot of these areas throughout the Caribbean and into the Gulf of Mexico. One thing that's been reported an awful lot is the image that this is one big, huge blob, 5,000 miles long, headed straight to Florida. And so that's what one message I'm really trying to get across here is that this is not one big continuous thing. It's lots of small patches and pieces, some of it getting pulled apart, some of it spreading in different directions. And what's heading towards Florida is not the main mass itself, but the part of it that's gotten to this part of the Caribbean and then getting shredded off by the ocean currents. So it's a much more complicated picture than I think what some of the reporting has said. But it's sort of a fascinating thing to see. A final question I get a lot is, so is this new Sargassum, Great Sargassum Belt a permanent feature? And the really big answer to that question is we simply don't know. There may have been strong negative NAO events hundreds of years ago that we just don't know about because we don't have the records, which may have created a similar situation, possibly. And maybe it lasted for 10, 20, 30 years before it finally died away. We just don't know. And we also don't know how much more man-made impacts, such as fertilizer runoff, may be affecting the belt this time around to help it to be sustained. So unfortunately, while we definitely have a lot of research to do, we can't answer that critical question, and we simply have to watch where the sargassum is and be prepared for inundation events as the sargassum is moving towards us.
Thank you, Rick. I love that you showed us this really good tool of how to see on a week-to-week basis how much sargassum is coming to the Caribbean. And if I understand correctly, this can be used also in other Caribbean islands, not just for the area you showed and with Mexico and Florida, right? Yes.
That's absolutely right. When you if you just Google sargassum inundation report, you'll find that the page that has that. And then if you scroll down, the first image is the one that's really Florida centric. But you scroll down and you see some of these other images that are showing you the Windward Islands, the coast of northern South America, and other areas.
Yes, that will be really, really helpful for everybody in the Caribbean. And I also love that you briefly talked about the big blob coming to Florida, because as much as I love that sargassum is in the news and people get awareness about it, and a lot of the news articles are actually giving a lot of good information, the title is just very misleading. And I've been using words you shouldn't use in front of children when seeing another one of these reports saying that big headline, while at the same time interviewing scientists who say, you shouldn't call it a blob, and then they choose the headline anyways.
Yes, that's right. And in fact, my laboratory has received kind of panicked phone calls from people who are planning to vacation in Florida saying, should I cancel my vacation because of this 5,000-mile blob that's attacking South Florida? And we're like, no, let's have a more subtle picture of what's going on here.
Wow.
I like very much how you explain the NOAA, this north oscillation of the Atlantic. I understood it completely right now.
Oh, excellent. That's good.
Really, yes. Thank you very much.
It's my pleasure.
Yeah, thank you very much, Rick. I think that's it for today. And thanks for coming back with us and doing this special recording. Thank you for tuning in today and learning with us from experts in the sargassum field. This course is made possible through funding by the Resilience, Sustainable Energy and Marine Biodiversity Program, RESMBID, financed under the 11th European Development Fund, EDF, Caribbean Overseas Countries and Territories Regional Program. RESMBID is being implemented by Expertise France, with the primary stakeholders being the 12 Caribbean overseas countries and territories. The course was designed by Franziska Elmer and Evelyn Salas, and the videos were produced by Marcel van der Kamp.